Well, hello everybody. As you've probably gathered from the title of the video, today I'll be determining the coefficient of static friction for a few different pairs of materials. Well, to be exact, we have four different pairs. First one is the steel and rubber. Then we have steel and plastic. Then we'll be changing the base. We'll have plastic and rubber. And lastly, plastic and plastic. But before we get into all of this, I will be giving a short review of how friction really works, and then I will describe my experimental setup, if it can really be called one. But anyway, let's begin.
Alright then, let's talk about friction. So we encounter friction a lot in our daily life. It's generally thought of something that slows things down or causes them to completely stop. But in order to carry out the experiment that we have in mind today, we'll need something more than just that. So we'll talk of friction in more mathematical terms. Generally speaking, we denote friction by this letter small f right here, and we say that it is directly proportional to n. Now, those of you familiar with this letter n or the quantity that it represents, we are talking here of the normal reaction. So, to help you understand it, I'm going to draw the ground over here, and then I'm going to place an object of mass m. Say, so it has a mass m here. Now, the Earth exerts a force that is equal to mg on that object downwards, right? So we'll say that the magnitude of this force or the value of this force is equal to mg. But Newton's second law tells us that if there's a force acting on an object, it has to have an acceleration. But we know that objects that are kept on a table aren't moving anywhere. They aren't moving up, they're not moving sideways, they just kept there. So to resolve this issue, we introduce a force called the normal reaction that the table exerts back on the object. So we say that this normal reaction, the value of this normal reaction is equal in magnitude to the force and is opposite to it. Yeah, I suppose this is supposed to be a straight line over here. As you can see, I'm not a very good artist. So we say that n is equal to mg. So this is generally true when the object is kept on a horizontal surface, but as we will soon see, it is not always true when an object is kept on inclines and things like that. So we have n is equal to mg over here, and this is also the reason why you feel weight. For example, if you are freely falling through the Earth's by virtue of the Earth's gravity, you wouldn't feel any weight because there's nothing pushing you back up. It is virtue of the normal reaction that you actually feel weight. Let's get back to friction now. So our experience tells us that we can't assign a definite value to friction. Now the reason for that is, suppose I apply a force F here, right? I'll apply a force of magnitude F. We see that the frictional force also applies another force that is equal in magnitude to stop the object from moving. Now suppose I increase this force to 2F, we'll see that the force friction again applies a force, say 2F, or we can just say F, that is to denote the force that is exerted by friction. And this keeps sailing. Suppose I change this to 3F, and this keeps on growing and growing until the friction keeps opposing the force that I'm applying in order to keep the object at rest. So the point that I'm trying to make here is that we can't assign a definite value to friction. However, we also notice that as we keep applying the force, we reach a threshold value after which the object can now start moving. That is, the force that I apply has finally become greater than this threshold value, after which friction can no longer apply a force. Well, so we instead choose to define friction in terms of this threshold value. Now we denote this threshold value by FL. Now this subscript L is used to denote the fact that it is called the limiting value of friction. You know what? Let me go down a bit over here. So we'll denote limiting friction by the letter F, and then we'll put a subscript L over here. And we'll say that it is equal in magnitude to nu. This is the Greek letter nu. And we have subscript S here to denote the fact that this is static friction. And we'll say that this into the normal reaction. So this term right here is the proportionality constant to make that proportionality up over here into an equality. And this is what we call the coefficient of static friction. And this is what this video is all about. So, or generally speaking, in fact, we say that the friction is less than equal to nu s into n. That is, this is the maximum value that static friction can have. So, as you might have already guessed, nu s is not a constant. It has different values for different pairs of materials. For example, it might have a value of, say, nu plastic and steel is equal to zero point 0.2, while say nu steel and rubber might have a value of 0.25. It varies, and we have no way to know what this value exactly is without determining it experimentally. So the question is, how does one go about determining this value? So from this figure up here, you might have gotten an idea of how we might do that. See, like, we keep applying this force until we reach the limiting value, and then we just divide it by the normal reaction rate. Seems simple enough. However, the problem with this is that there's no easy way to know how much force I'm applying with my hand. I can't randomly say that no, that I'm not applying 10 newton or I'm applying 100 newtons. It's very difficult to quantify how much force it is that I'm applying with my hand. Alright, to overcome this problem, so we'll use inclines. So suppose this right here is an incline, right? And this angle, and it is inclined to the angle at an it is inclined to the horizontal at an angle theta, right? And we are also going to place an object of mass m over here. Just let me get this proper. Yeah, that's it. So it's not exactly a cube, but we get the gist of it. So we're going to say that this object has a mass m. Now we're going to assume that theta is the angle at which the object that is kept here will just start to move down the incline. Now, of course, this might not be the case, that it might not. We have no way of knowing that this is in fact the angle theta, but we assume it. We do this so that we can use the force of limiting friction so that we can have a definite value for friction up here. Next thing to do here is to show what are the different forces that are acting on this body right here, body of mass m. So we know for sure that there's a force mg that is exerted by the earth that goes all the way down over here, right? It's going to be vertically downwards and it's going to be equal to mg. Now another feature of normal reaction is that it acts perpendicular to the surface. So normal reaction won't act along this direction, but in fact it will act along this direction. That is, it's going to be perpendicular to the surface. And so we don't know the magnitude over here because it is not directly opposing the force mg. Say if it were to go in this direction, then yes, we could have just said that it is equal to mg and it would have been that's all that we would have to write. But here we will only say that the magnitude is equal to n. We don't know that, and we'll be evaluating it. And the friction will act in this direction because the weight of the object will be trying to pull the object down the incline, so the friction will be acting parallel to the incline and in the other direction. So we'll write FL over here. So another thing to remember here is that we're dealing with vectors, so we can't just add these forces up and say and apply Newton's second law, because that's not how it works. So we'll have to resolve these vectors into components. So we here have a triangle over here, and we can say that this angle right here is 90 minus theta. Okay, and then we are going to extend this line over here. This is supposed to be a straight line, and since this line is perpendicular to the surface, this whole angle is going to be 90 degree. Alright, so what we're going to do is that since this whole angle is 90 degree, we're going to denote this angle by theta, right? And we're going to complete this right angle triangle. It might not look like a right angle triangle, it definitely does not, but this is a right angle triangle, I'll show you. So this is 90 degree over here, this is theta. So for those of you who have had some trigonometry, you know that this side over here would be mg, that is the force that the earth exerts, into cos theta in this direction, and the force in this direction will be mg sine theta, right? And we can denote this force here. We can say that this mg sine theta is over here, it's parallel to the incline. So although the actual force mg is neither parallel nor perpendicular to the incline, we can resolve it into components such that we get one component that is parallel to the incline and one component that is perpendicular to the incline. And now we can apply Newton's second law in both the vertical and horizontal directions. So we can say here that FL is equal to mg sine theta. Alright, this will be our equation 1, and we can also say that n, now we can equate this n to mg cos theta. Alright, so now we can divide first equation by second equation, so we can write this as 1 divided by 2, right, is equal to tan theta, and this is equal to FL by n. Now what is FL? FL is nothing but nu s into n. That's right. So nu s by n is equal to tan theta. So here we have a relation that does not depend on what the mass of the object is. It does not depend on what force is being acted on it. All it depends on is the angle at which this object just begins to slide down the incline. And so this makes evaluating the coefficient of static friction very easy. So all you have to do is make an experimental setup that sort of resembles what you want to do, and then find this angle theta. And this angle theta is, we denote as subscript r here. We say that this angle is called the angle of repose, the angle at which it just begins to slide down the incline. So we'll put this over here as well. So this was a brief review of friction, and so we'll get into the actual experiment right now.
Well, hello and welcome back, guys. We are going to proceed with the experimental part of this video. So like I had talked about in the beginning, we have our 4 objects right over here, and we are going to use them to determine the coefficient of static friction. So, but along with these, we also have books over here. Now, these are going to serve as our height. We are going to vary the height, and the width can be varied by simply moving the scale like this. So what that's going to do is that's going to give us the tan theta value, because I can measure the height with this scale over here, and I can measure the width with again with the scale, and then I can take the ratio to find tan theta. Before I formally begin, I think a disclaimer has to be given, because what I'm doing here today is not at all scientific. This is just something that I'm doing because I've got nothing to do and I've got a free afternoon. So, and I'm not taking into account any errors that might pop up. I'm just taking two values that will come and I'll take the ratio of them and get the tan theta and thus the coefficient of static friction. So please do take everything that I do today with a grain of salt. So with that said, we will do the first pair of objects, that is steel and rubber. So just to get a preliminary value over here, I'm going to remove this stack of books and then I'm going to place the scale over here and I'm going to see whether the rubber piece falls down or not. Well, it didn't. So now what I'm going to do is I'm going to keep adding more and more books such that the height increases, and if the height increases the tan theta value will increase, and I'll keep doing this until I reach the angle of repose, and when I reach the angle of repose I will take the tangent of that angle and I will get the value of the coefficient of static friction. So since it obviously isn't moving, I'm going to add another book and see if it moves then. So with one notebook on top, let me see if the rubber piece is moving. So I keep the rubber over here and it is moving. Let me just make sure. And you can clearly see that it is in fact moving. So I will measure the height for this value and it's going. So the height at this point, it appears to be about 14 centimeters and the width is exactly 20 centimeters. So we have gotten our both height and our width, and then we can take the ratio to get tan theta, which, since this is the angle of repose, would be the coefficient of static friction. So with that we have finished our first pair of objects, that is steel and rubber, and we'll be moving on to steel and plastic. So let's begin with the steel and plastic. If I put plastic piece over here, I see that it will slide straight down quite fast. So I think I need to remove quite a few books over here. So I'll remove these two books and then I'll try again. And let's see if it goes down now. It isn't going down, so I will take a small book and put it over here and see what happens then. Alright, so it still isn't going down noticeably. Okay, I guess I will take this measurement. Yeah, it is going down at this point. Yeah, it is going down. So I will take the height at this point. The height at this point is around remember, I'm taking the height at this point, so that would be, I guess, around 11 centimeters, and this is actually significant more the width. It's close to around 22.25 centimeters. So that's our second case of steel and plastic. Alright, then we will now be moving on to our third case, that is of plastic and rubber. So let me just put this rubber piece over here and see if it moves, and it is actually moving. Let's see. Yeah, it is actually moving. So let's just remove a book and make sure that that is not more than the angle of repose. So we are going to put this piece over here and it's clearly not moving, so we're going to put another notebook over here and check. So I'll have to hold this here because the scale is actually moving, because the coefficient of friction for wood and plastic is probably less than that of plastic and rubber, so the scale is moving earlier than the rubber. So it's still not moving, so I'll add two notebooks and let's see what happens then. So is it moving then? Is it moving now? It's not moving, so let me add a few more notebooks. I have a lot of notebooks over here. So that's one more notebook. Let me just do one for now and let's see what happens. It's still not moving, so let me just add another notebook over there. And is it moving now? Yeah, it does actually appear to be moving, and I think that right there can be taken as our angle of repose. Let me do the measurements. We have this thing right here to be, the height is around 10 centimeters. Yeah, I think that seems about right. Oh no, my bad. I'm not actually measuring this properly. So yeah, I mean, so you understand why I put the disclaimer in the beginning of the video, because my experimental skills are absolutely horrible. So it's around 14 centimeters here, and this is about 22.5 centimeters. So that concludes our third case. Alright then, we'll be moving on to our last case, that is plastic and plastic. I expect this to be the one that has the least coefficient of friction, because I think the ratio, because these are both very smooth materials. So let's see what actually happens. So if I keep the piece here, does it slide down? It doesn't actually. Let's see why. Oh, it does actually slide down. Yeah, it does actually slide down. So I'm going to remove one book and see what happens next. Does it still slide down? Just check again. No, it doesn't actually slide down. Yeah. So let me put let me put a few notebooks and check what happens next. So if I put one notebook, what is the value that I get? Oh wait, sorry, my bad. And no, is it moving? It's quite unpredictable. Oh, it's actually moving, yeah. Oh yeah, it's actually moving. So let me just check it once more. Okay, yeah, it is moving. So let me take my scale over here, and this value right here is oh, it's just 9 centimeters. Like I said, this value is quite low, and this value over here is actually 26 centimeters. So that is all the cases. Let's now go to the Excel file that I've made here to check out what the values of the coefficient of friction actually are. So let's go.
For some reason, I wasn't able to record Excel, so this is actually a screenshot of the Excel file. This is the last step of whatever we did today, if it could be called an experiment. So as you can see, the coefficient of static friction is simply tan theta, which is the height divided by the width. And so we can see the values over here. The steel rubber has the highest, while this plastic has the lowest, which is which is to be expected, because plastic feels much smoother and rubber is also quite, well, it feels quite rough. So you can get an intuitive understanding from this. But the purpose of my making this video today was that science doesn't always need to be done in high-tech laboratories. You can do it just sitting in your home. You just need to have that spark within you. And with that, I think I would like to thank you for sitting through, I think, what is 20 minutes of me blabbering on. Well, if this gets a positive reaction, I might think of making a few more videos. So let's see. Thank you.